In this video, we solve this truss problem. This problem is taken from another video, Force Method for Analysis of Statically Indeterminate Truss. So you can have a look at this video also. It shows how to solve this problem using the force method. But in our video, we will solve it using the method of Stroops. Basically, you have these joints A, B, C, D, E, and you have members AD and BE, which cross. There's no joint where they intersect here. The supports are at B, which is hinged. It's free to rotate, but no horizontal or vertical displacements. At E, you have a roller support, so it's free to move vertically but not horizontally. The loads are shown 8 kilonewtons at C, 12 kilonewtons at D, 8 kilonewtons at E. It is externally statically determinate because you have a hinge joint here and it's on rollers here. Internally, it's indeterminate because you have this stroop, as we will call it, formed by the joints A, B, D, and E, and these 6 members. So we will proceed with the method of Stroops. We will analyze this structure using the method of Stroops, which I developed in my video, Trusses, Electrical Circuits, and Kirchhoff's Laws. So if you have not seen this video, you can view it before going ahead, or you can come back to it. But the steps that I show in this video should be easy to follow without previously viewing this video. First, we do the transmission of the external forces to the supports. Now let's look first at the 12 kilonewton force vertically at D. This can go straight through to the support at B, and then this member will be in compression. Compression is denoted by negative signs, so you have negative 12 kilonewtons in this member BD. Now for the vertical 8 kilonewtons at C, you must have a vertical component to balance that. So since this is horizontal, it will not contribute any vertical component here at C. So the vertical component comes entirely from this member here. So this member BC must be in compression also, at a value of negative 8 times root 2. So that will balance the vertical 8 kilonewtons. But for the horizontal equilibrium, this force of 8 kilonewtons in this direction must be balanced by a force of 8 kilonewtons horizontally at C. So DC will be in tension at a value of 8 kilonewtons. Now you have 8 kilonewtons pulling to the right at D. You must have an equal force to the left here. So this member ED will also be in tension at 8 kilonewtons. Now you have a vertical force of 8 kilonewtons here. The 8 kilonewtons here will not contribute any vertical components. So you must have a force in this direction at E coming from this member. So this member BE will be in compression minus 8 square root of 2 kilonewtons. Of course, you have a ruler here at E, so the reaction here will balance the other horizontal components. Now at A, there's no restraint or anything. This is free to move. And yeah, I think we've taken care of all the external loads here. So the other member forces can be 0. In all of these you can have 0. In these 3 you can have 0 force. So this completes the transmission of external forces to the supports. Okay, we have obtained these values in the members. Now we identify the Stroop in the previous diagrams. There's just one Stroop in this structure, A, B, D, E. So the structure has 1 degree of indeterminacy, and this is the Stroop that it contains, A, B, D, E, with these 6 members. As we've done before in previous videos, the Stroop forces we can take as F on the sides and minus F root 2 on the diagonals. Again, we do not put arrows here because the F can be either positive or negative. We are not specifying F to be positive or negative. So positive, of course, indicates tension. Negative will indicate compression. Okay, so the F could be negative here or here also. Now the superposed forces. We superpose the forces from the 2 previous diagrams. We are just concerned with the Stroop here. The members outside of the Stroop will not change due to the Stroop forces. So remember, we had a force of 8 kilonewtons tensile in ED plus the Stroop force F. We had a compressive force of 12 here, negative 12, plus F will be the combined force in this member. On the diagonal here, negative 8 root 2 minus the Stroop force minus F root 2. Minus F root 2 here, F and F. These are just the Stroop forces because it's 0 plus the Stroop force. This just shows the relative lengths of the members. You can take the side of the square to be 1 unit. So it's 1 on the sides and then square root of 2 on the diagonals. As we've done in previous videos, and again this is explained in the video on trusses, electrical circuits, and the Kirchhoff's laws. The compatibility equation for this type of Stroop is a rectangular Stroop. In fact, this formula, this compatibility equation, can be shown to be valid for any parallelogram type Stroop. So it's the sum along the perimeter members, the length of the member squared over cross-sectional area times the force in that member. I should put subscripts here, but these differ for each member. And then you have the same summation of the similar terms on the diagonals. Now in this problem we assume A times E is the same for each member. Theoretically I should have E in the denominator here, but I'm assuming the material is the same throughout, so I've just cancelled all of the E's. So if AE is the same for each member, then A is the same for each member, and you can also multiply by A throughout and clear the denominator. So this compatibility equation reduces to this. The coefficients are simply the squares of the relative member lengths, L squared times the force in each member. So here I'm indicating the coefficients on the diagram itself. I'm not making up a table listing the members and the coefficients. I'm just showing the coefficients on the diagram. It's the squares of the relative member length, so 1 squared, 1 squared, 1 squared. And then on the diagonals you have root 2 squared, which is just 2 on each diagonal. Here I am just copying and pasting the previous two diagrams. This is the diagram with the coefficients, and this is the diagram with the superposed forces. So the idea here is to multiply the coefficient times the force on corresponding members and add those. Okay, so it's the sum on the perimeter equal to the sum on the diagonals. So the compatibility equation will be this. Okay, you can verify this. These are the coefficient times the force on the perimeter, and on the other side you have the coefficient, which are both 2 times the combined force, the superposed forces on the diagonals. And you can simplify this equivalently. You have 4f minus 4 on the left hand side equal to minus 16 root 2 minus 4f root 2 on this side. Divide throughout by 4, you get f minus 1 equal to minus root 2 minus f root 2, which is 1 plus root 2 times f in equal to this thing. You can solve for f, you get f equal to minus 9 plus 5 root 2. So once you obtain f, you can substitute into the combined force diagram, and you can get the forces in all the members. So this is the solution for the forces in the Stroop A, B, D, E. I've given the exact values, leaving everything in terms of square roots. And we can look at the overall solution also. So here is the entire truss. I've included the joint C also. And I've given the forces here in decimal form. It's probably easier to get a sense of the size of these forces. And notice here that you have an external force of 12 kilonewtons, which is transmitted through this member BD to the support at B. In this case, the 12 kilonewton compressive force is increased to 13.9 in BD. That's due to the influence of these Stroop forces. Okay, because of the redundant member here, you have this increase in the compressive force here. Of course, you have a decrease in the tensile force here, in DE, which was originally 8, now is 6.07. You have tensile force in AD and a compressive force in BE. So these are the overall forces. You can verify in the video that we referred to before, you can verify that this solution obtained by the method of Stroops is exactly the same solution given by the force method. You can look at the other video that I've mentioned and see that both methods give exactly the same results. Now, as usual, I like to give a little extra analysis because I believe that my method of Stroops with the form of the compatibility equation can give you some additional benefits, not just in analysis but also in the design of these indeterminate structures. So let's suppose the cross-sectional areas were these. You had equal areas at the top and bottom, A1, A1, equal areas on the left and right sides, A2, and equal areas on the diagonal, A3 on each diagonal. So suppose we wanted to generalize, instead of restricting ourselves to equal areas for all the members, we wanted to have 3 different cross-sectional areas, top and bottom, left and right, and on the diagonals. Now in that case, the coefficients of the compatibility equation would be these. Remember, it's the relative length divided by the cross-sectional area. So the coefficient would be 1 over A1 here, 1 over A1, 1 over A2 here, 1 over A2, 2 over A3 on each diagonal. So these would be the coefficients, and then we use these coefficients together with the superposed forces to get our compatibility equation. So here we have the coefficients. These are our superposed forces. Remember what we do: multiply the coefficient by the corresponding force. The sum on the perimeter should equal the sum on the diagonals. And this is what we get here. This is the sum on the perimeter. You have 4 terms here, and then 2 terms for the sum on the diagonals. So of course, I'm just using A1, A2, A3 as variables here. This simplifies to this. You divide across by 2, it comes down to this. And here we multiply by A2 over 6 minus F on both sides. So it comes to this form: A2 over A1 over this denominator plus A2 over A3 over this denominator equal to 1. So notice here we have the ratio of these 2 areas and the ratio of these 2 areas. The denominator is in terms of F. If we wanted F equal to -2, you can just check the previous solution. We got a value of F that was fairly close to -2. But suppose we wanted to get a value of F equal to -2, which is close to our previous solution. And suppose we wanted to arrange for that by choosing cross-sectional areas in an appropriate way. So just plug in f equal to -2 into the denominator on the previous slide, and we'll get this equation. Okay, notice the a2 over a1, a2 over a3, these are both positive quantities, and it's a linear equation here, so this can be represented by a straight line. And here is our straight line. We can plot a2 over a3 against a2 over a1. It's a straight line. You'll have 4 on one intercept and square root of 2 on the other intercept. So it's a straight line through these points. a2 over a1, these are the ratio of the areas of cross-section on the two sides of the rectangle. You want a2 and a1 to be fairly close to each other. In other words, you want a ratio close to 1. For a2 over a3, remember a3 is on the diagonal. You want the diagonal to be smaller than the cross-sectional area at this side. So you want this ratio to be a little greater than 1. So you can pick a point about here which gives a value a2 over a3 greater than 1. So a2 greater than a3. And a2 over a1 less than 1. So a2 would be less than a1. So again, in the design of the truss, you can look up lists of cross-sectional properties of steel members if you're using steel, and try to find ratios of members close to this value and close to this value, and in that way you'll get a force, an F, close to -2. So this is a way of designing the structure. In other words, choosing appropriate ratios for the cross-sectional areas. Now let's look at another scenario. Suppose we wanted f equal to 1, then that equation would become this. If we put f equal to 1 in the denominator, we get a2 over a1 equal to 3 over 2. a2 over a3 divided by 3 over 4 root 2 equal to 1. Now here, both of these are positive, so each of these terms must be less than 1. So the a2 over a3 must be less than the 3 over 4 root 2. Now, as we said in our design, we would like the diagonals to be a little smaller in cross-section than the size of the rectangle. So if the diagonal is smaller, then this ratio would be greater than 1. But here we have it less than this thing, which is less than 1. So this may not be desirable. We don't want an a3 larger than the a2. So again, you can try different values of f and see if it allows convenient values for the ratio of cross sections. Let's look at this equation we obtained before, where under the given loading we obtained this for our compatibility equation. We expressed it in this form. Here what I'm doing is I'm making a table. I am putting in different values of f, and I am obtaining the two denominators here. Okay, so the a2 over a1 will be over this, and the a2 over a3 will be over this. That's for f equal to 0. You can go through this and pick out a convenient value of f that will give you sufficient choice in your ratios of cross sections. So for example, we looked at this case here when f was -2. We saw that you had 4 and 1.4 on the two intercepts of that straight line. If you went to further up to -2.5 for f, you'll get these values. So you'll get more flexibility here because you have a larger choice. Remember, the a2 over a1 would have a maximum value of this. The a2 over a3 would have a maximum value of this. So you'd get more choice in your ratios for the cross sections. If you went down to -1.5, again the denominator here would be smaller, and the denominator here would be smaller. So this would be a more restrictive choice of values. So here the a2 over a3 is restricted to 1.06. So this may not be convenient for you to be too restrictive with this value of a2 over a3. So the -2 or the -2.5 may offer you more flexibility, more choice in the ratios. But this is just hypothetical, of course. I'm just asking you to consider this as a guide when you are designing these types of indeterminate trusses. You can use the compatibility equation not just for analysis but also for design of the sections. Once again, I thank you for viewing this video, and I hope you will compare the method of Stroops with the force method used in other videos on this topic. So I hope you will obtain some benefit and a greater understanding of indeterminate trusses from this lecture. Once again, I want to thank the University of the West Indies for its support in my video creation, and I ask you to follow me and look out for future videos. I'll be doing more on indeterminate trusses, and we will look at externally indeterminate trusses also, and go on to other topics. Thanks again for your attendance.